Welcome back to Bio 6612. Today we're going to talk about inference for parameters and logistic regression. In particular, we'll cover confidence intervals for parameters, hypothesis testing, and briefly talk about predicted probability. So generally, we want to calculate confidence intervals for our coefficients beta in logistic regression, where the estimate for beta is the log odds ratio. And this is calculated using a maximum likelihood estimation. Because MLEs have an asymptotically normal distribution, we can use a normal approximation to construct confidence intervals with a formula that looks like this, which is the same as you've seen before for linear regression, where the confidence interval is constructed by beta hat plus or minus 1.96 if you have alpha equals 0.05 times the standard error of that estimate. And this is the walled confidence interval. So if you want to construct this confidence interval, where do you get these standard errors? Well, they can be obtained in R, just like you can get estimates for your beta hat itself. So the previous slide gave you a confidence interval for the log odds ratio. But generally speaking, we interpret things in terms of the odds ratio. Luckily, to get a confidence interval for the odds ratio, all you have to do is exponentiate the confidence interval for the log odds ratio. So in this green box here, that's the lower bound for the log odds ratio. Just exponentiate that to get the lower bound for the odds ratio. So I'm going to bring us back to our example from lecture 2. In passive smoking, basically we wanted to know if passive smoking, also known as secondhand smoking, is associated with lung cancer. And in our data, there's the variable passive, that's 0 or 1, indicating exposure to passive smoking. Y is the number of cancer cases, and N is the total number of observations. Here's our data here. I'm going to build a model in R called smoking mod. And this is a model where we're just looking at the outcome against that variable that's an indicator of passive smoking. Here, where passive equals 1 if you have had exposure to secondhand smoke, and 0 if you have not had exposure to secondhand smoke. And so just looking at the estimates that are produced by that model, we have this table here, the estimate column, that's your betas. You have the intercept, that's beta 0. You have passive, that's beta 1. And these are your values here, beta hat. Those are the MLE values for those parameters. And then you also have the standard errors here. So that's going to be your standard error hat of beta 0 hat and your standard error of beta 1. And they also give you a Z value here and a P value. And that P value is actually constructed using the walled statistic as well. So let's use these standard errors to construct some confidence intervals. From the previous slide, we have that beta hat is 0.493 and that the standard error for that beta is 0.128. So we can construct the confidence intervals using the walled statistic by taking that estimate, that beta, and then just subtracting 1.96 times that standard error, and then exponentiating that estimate, the lower bound and the upper bound, to get the confidence interval for the odds ratio. And if you look here, those terms are printed, or you have the odds ratio and then the lower bound. So you would have, for the odds ratio for passive smoking, would be 1.64 with the bounds 1.28 to 2.1. And I did it out this way to show you sort of that the odds ratio and its confidence intervals are calculated using this Wald statistic. However, an easier way to code that is just to use this piece of code that's written here, and you'll get exactly the same results if you just take this function confident and then of the actual naive of your model that you've run it, and then exponentiate that. So for the log odds ratio for beta 1, we would say that we're 95% confident that the true log odds ratio of lung cancer comparing those exposed to passive smoking comparing to those not exposed is between 0.24 and 0.74. And for the odds ratio, confidence interval, we would say we're 95% confident that the true odds ratio of lung cancer comparing those exposed to passive smoking to those not exposed is between 1.28 and 2.1. Okay, so next is hypothesis tests. And I'm going to give you a general template for conducting a hypothesis test that I'd like you to follow. Where the first step is to explicitly define the population parameter of interest. If you're looking at the odds ratio, then that's going to be the exponentiated beta coefficient. I want you to state the null and alternative hypotheses. Common one might be the null hypothesis that beta 1 is 0 versus the alternative hypothesis that beta 1 is not equal to 0. State the significance level of the test. Usually we have 0.05, alpha equals 0.05. State any necessary assumptions. Those are going to depend on what sort of test you're doing. But often when you're doing modeling, those are going to be the assumptions of linear or logistic regression. State the form of the test statistics and its null distribution. State the decision rule and the p-value, and then state your conclusions in the context of the problem. This is your interpretation of your results. So we're going to walk through a hypothesis test for the passive smoking example. So we're interested in studying the relationship between lung cancer and secondhand smoke, or also called passive smoking. First, we define our population parameter of interest. In that case, we're interested in beta 1, the true population level log odds ratio describing the association between exposure to secondhand smoke and lung cancer status. And this is in a model where we have the logit of the probability that yi equals 1. So the probability that the ith subject has lung cancer is equal to beta 0 plus beta 1 times passive, where passive is just a 0 or 1, depending on exposure to passive smoking. Then second, we state the null hypothesis. Here, a null hypothesis of beta 1 equals 0 would indicate no association between passive smoking and lung cancer, versus an alternative hypothesis that beta 1 is not equal to 0, meaning that there is an association, but we don't know whether it's a negative or a positive association. We're going to choose alpha equals 0.05. And then the assumptions of logistic regression are that your observations are independent, you have a sufficiently large sample size, and that your model is correctly specified. So in general, when I say correctly specified model, what I mean is that you don't have any unmeasured confounders that you aren't accounting for, and we're going to talk about confounders in the next couple lectures, and that there is a linear relationship between the covariates x and the log odds of y equals 1, and we're going to talk about how to check some of those assumptions in a couple other lectures as well. These should be steps 5, 6, and 7 of your hypothesis test. So in step 5, we calculate the test statistic, which is 3.86, and with a p-value of 0.001. So what's the form of the test statistic? I'm just going to tell you right now that it has a normal 0, 1 distribution under the null hypothesis, and I'm going to show you why I know that in the next couple slides. And then since the p-value is less than 0.05, we would reject the null hypothesis. And in the case of this problem, that conclusion is that we have sufficient evidence to conclude that lung cancer and secondhand smoke are associated at the 5% level. Basically, those exposed to secondhand or passive smoking have about 1.64 times the odds of having lung cancer as those not exposed to secondhand smoke. And that's the odds ratio interpretation. So again, how did I know that the test statistic had a null distribution that was normal? Well, from lecture 2.3, we talked about the Wald statistic, and in its normal distribution form, it looks like this, where you have your estimated parameter of interest, the subtracting the parameter value under the null hypothesis and divided by the standard of the standard error for that estimate. And so the test statistic given in R is 3.86 with a p-value of 0.0001. And we can actually use this test statistic and calculate a p-value using the standard normal distribution in R to check that if we assume it's a standard normal distribution and we use this test statistic, do we get the same p-value that our output? This is the p-value output by our model. And that's what I've done right here, actually, is I've just calculated that p-value manually for the test statistic using the test statistic of interest using the p-norm function, which is the probability distribution for a standard normal variable. And it gives us a p-value of 0.000111. And just checking against the p-value returned by our model, those are the same. So yeah, it actually is the case that our test statistic is coming from a standard normal distribution. So that's telling you that R is using the Wald test to calculate the confidence intervals and the p-values for your parameters, which is a good thing to know. And SAS does the same thing, actually. SAS also uses the Wald statistic, but it uses the chi-squared version of that statistic rather than the standard normal version like we're using here. So another thing that's nice about logistic regression is the ability to get probabilities, predicted probabilities out of the model. And the way that we do that is by just solving for pi I in this equation here. And what you end up with is e to the x beta over 1 plus e to the x beta. And then for anybody who has, say, a certain set of x value, for any individual, then you can get an individual predicted probability based on their estimated coefficient values, which you would plug in here, and their individual x values. And it's good to note that the interpretation of this quantity is a little different depending on what your study design is. So for prospective designs or cohort studies, this p-hat is an estimate of the incidence of disease. For cross-sectional studies, p-hat is an estimate of the prevalence of disease. For case control studies, p-hat is often not interpretable unless the sampling fraction of cases and controls from the reference population is known. And that's almost always not the case. So what about in our example for passive smoking and lung cancer? What's the predicted probability? So the equation for that would be for any given individual, pi I, let's say given some set of x values, is e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. So what's the predicted probability of lung cancer given exposure to secondhand smoke? So when you're exposed to secondhand smoke, your x value is going to be equal to 1. And so what you would plug in for this equation is your estimated beta 0 and beta 1 hat values, and then just your x value would be equal to 1 here. And you can calculate that using, so that's what I'm doing here. I'm multiplying the coefficients times the, and this is using sort of a matrix multiplication style. And I encourage you to walk through this code yourself. So I'm multiplying 1 times beta 0 here plus 1 times beta 1. That's what's going on with this code. And then to get the predicted probability for somebody who is not exposed to secondhand smoke, those are the people where xi equals 0. Well, in that case, in this equation up here, the xi would be 0, so this part of the term would drop out, and this part of the term would drop out. So, and that's what this code is saying here, okay? It's saying, all right, now we want to take the two coefficients, beta 0 and beta 1, and we want beta 0 plus times 1 plus beta 1 times 0. That's that, having that 0 here will cause that beta 1 term to drop out for the people who are not exposed. And so then you can use that, you can to sort of by hand calculate your predicted probabilities. And this will give you, for the exposed group, the predicted probability of lung cancer is 0.57, and for the unexposed, it's a bit lower, it's 0.45. And the interpretation is down here, but just so you know, I did this all sort of following the equation that I gave you to show you how you can extract the parameters that you got in your model to plug in and find the predicted probability. But there's a much easier way to do that in R, and that's just using these fitted values, accessing these fitted values that are returned by your model. Or you can use this predict function. And for the predict function, you could even give it new potential patients with different x values and then get a predicted probability for that new subject.